Welcome to our lecture 18 of Engineering Mechanics Dynamics class. We are in the chapter Kinetics of Particle, Impulse and Momentum, chapter 15. And today we're going to talk about angular momentum. As you can see in the image, it's a satellite. Satellite always rotate around the Earth, so it has always an angular. It moves in a curved path and creates an angle of movement around the Earth, so it can have a angular momentum. And we already talked about momentum in your previous class. When momentum was a scalar, it was the multiplication of mass. It was the multiplication of mass and velocity. But today we're going to talk about angular momentum, which would be a little bit different than that. So let's see what our learning objective is. So today's learning objective is define angular momentum and develop relations between moment of force and angular momentum. So in this lecture we're gonna cover this part, and to keep the video short, this part, the relationship between momentum force and angular momentum will be covered in a second lecture, so you have a small segment to cover. So again, for example, you can see a running track where people are running in a curved path. It's mostly all running tracks are circular or oval shape, so you will have angular momentum. So when we talk about just momentum, then it's just scalar multiplication of your velocity and mass. When we talk about angular momentum, it has to be from a point. So we're going to talk about that more. Another example could be this slide. Again, the slider has to start from here, and he has to slide in an angular path to come down here. So about any point you will have point here, you will have an angular momentum. So these are kind of application. So let's see how can we define angular momentum. So angular momentum the angular momentum of a particle has it's about a point. So let me draw an XYZ coordinate. So XYZ coordinate, and we can have a particle moving along a plane. So we have a particle and it's moving only on XY plane, so only on XY plane, and it has a movement only on that plane. So the angular momentum is defined as the moment of the particle linear momentum. So you know, how do we find moment of a force? So you have a force acting on this direction, you want to moment from this point. What you do, you just have the force multiplied by the perpendicular distance. I guess it's not perpendicular. The perpendicular distance would be the shortest. So if it's d, then moment of that force is fd, correct? So for angular momentum, we have to use almost the same concept. We will have the linear momentum that is mv multiplied by shortest distance. So since it is same way that we found our moment, the angular momentum is also called moment of momentum, and we'll see in a while why. So like we said, the angular momentum has to be from a point, it can be any point. We're taking the origin. So the perpendicular distance of the particle, which is the shortest distance, if we say this is d and the mass of the particle is m and it is moving at that instant with a velocity v, so the angular momentum h, so we define angular momentum by h, it b equals to d, the scalar version, mv. So this is the momentum, and when you multiply with the distance, so this is the moment of a momentum. So the other term of angular momentum is moment, M-O-M-E, moment of momentum. So other way you can remember, you just have to take the moment of a momentum to get the angular momentum. So the unit of momentum is kilogram. So you can see from here we can have the unit as unit of distance is meter, unit of mass kilogram, and unit of velocity meter per second. So we can get the unit as a kilogram meter square per second. So this is how we get the unit of angular momentum. So angular momentum can be formulated in two ways. One is scalar formulation, and we can also formulate the same angular momentum in vector formulation. So the one we just figured out here, h, we did not consider any direction, so this is the scalar form, the magnitude of angular momentum, just distance multiplied by its mass and its velocity. This is the scalar formulation of angular momentum. So the angular momentum has a direction. So the direction of angular momentum HO is defined by the right hand rule. So if this is the direction, and my particle is moving in this direction, so we will have angular momentum. The direction will be using your right hand. So this is moving in this direction. If you use your right hand here, if you place it here, if your finger direction, the curve of your finger would be the curl of your finger would be if you put the curl of your finger here, direction of the velocity, your thumb will show the direction of your angular momentum. So in this case, our particle is moving in this direction. I put my thumb along that direction, and my thumb says the direction of my angular momentum is along z-axis, perpendicular to the plane where the particle is moving. So so this is all about the scalar formation. Let's talk about the vector formation. Vector formation of the angular momentum. So for vector, we assume that instead of the xy z plane, xy on the xyz coordinate, instead of the xy plane, now my particle is on a space. So it's not on any plane, it's just on the space. and it is moving along a path. We know the velocity is always tangent at that point, so my velocity would be v and momentum would be mv. It is along that direction, and my angular momentum about origin, it could be any point, we're taking here only from origin. So the position vector from origin to the particle is r. So if that's the case, and we know, and we saw in previous slide, that the angular momentum is perpendicular to the plane that is traveling. So if it's traveling in this direction, in mv direction, and you have the position r, so the direction of the angular momentum would be perpendicular along your according to your right hand rule. So it will be this direction, and the angular momentum would be HO. So how do we define HO for vector formation? HO, which is vector, equals to R vector cross product of mv, and v is also a vector, because you can take vector product on a scalar and vector. It has to be vector on both sides of a vector product. So the angular momentum would be perpendicular to the plane covered by r and mv. So maybe this area. So at this instant, the area is the position vector r, and then the small amount of the curved path, and your momentum will be perpendicular to that plane. If it moves a little bit, then you have a new plane, and it will be always perpendicular that plane that is covered by. So just to clarify, so the direction of the angular momentum is the perpendicular to the plane containing r and mv. So this is the vector formation of the angular momentum. We can also write this angular momentum in matrix form if we have the directions in I, j, and k. These are all vectors, unit vectors, and rx, ry, rz, and mvx, mvy, mvz. So this is the matrix form of the vector formation of the angular vector. This is just if you take components of r, which is, for example, ri, or plus r rxi, ryj, and rzk. So I'm just splitting those in xyz coordinate, and you will have the cross product, and we will also have the component vxi plus vyj plus vzk. And when you split the r and v in these xyz components, then you can write the same angular momentum in matrix form, and it is easier to solve and apply. So that was all about angular momentum. We had seen, in summary, we have seen the scalar formulation, which is angular momentum about a point which is defined by the distance, perpendicular distance from that point O and to the momentum mv. This is the scalar one, and we also had the vector one, which is defined as the vector position cross product to mass and vector of the velocity. So in next class we're going to talk about relation between moment of a force and angular momentum. Till then, see you.